Here we have another example in which you're asked to verify an identity. An identity is really just an equation, but we're asked to verify it. And that's why I always like to put a little question mark over the equal sign to say, well, is it true that 1 minus cosine over sine is equivalent or equal to sine of x over 1 plus cosine of x? Are these two things equivalent? Now, in verification problems, they're usually rigged to work. They are true, they are identities, and your job is to try to verify. And so really, in order to verify, you want to show that the left side and the right side look identical. And the way in which we do verifications is, first of all, remember, we're going to take every trig value and turn it into sine and cosine. We're going to bring in different tricks we've learned from algebra, things like common denominators, what to do when you're dividing by a fraction, how you can invert and multiply. Things like factoring and canceling. I know Dr. Hayden is not a fan of canceling, but I'm going to use factoring and canceling. Another thing called the idea of conjugates, which maybe you know a little bit about, but it turns out this problem right here, use of conjugates is a pretty good idea. And then, of course, Pythagorean identity, specifically sine squared plus cosine squared equals 1. All of these ideas are kind of brought in to when you try to verify a trig identity. So let me move these aside, and let's talk a bit about how we would address this problem right here. Now, one thing you could do is you could graph this on Desmos, say y equals this and y equals this, and you'd find out that the graphs are exactly the same. So that's kind of sort of visually verifying it or graphically verifying it. We're going to try and algebraically verify. So again, the first thing we always try to do is we convert all trig values to sine and cosine. Well, you look at it and you say, well, shoot, everything is already expressed in terms of sines and cosines. So this really isn't going to help us much at all. So we'll just kind of set that aside. And so now we want to think about the different tricks we might use, algebraic tricks. Factoring and canceling is going to be pretty tough to factor these. Conjugates, common denominators, well, maybe if we could get these to have the same denominator, maybe we could show that they're equivalent. And then we're not really dividing by any rational values here. So we're kind of in a tough situation. This is a pretty challenging problem. and so let's talk a bit about, first of all, something else, by the way, you cannot do. You cannot simply do sine squared, sine times sine is sine squared. And then this times this, which would be 1 minus cosine x, 1 plus cosine x. Now, if you did that, okay, what you'd have, you'd multiply this out. This would be 1 plus cosine minus cosine. Those cancel. And then you have minus cosine squared. And you might recall, oh yeah, the Pythagorean identity, sine squared plus cos squared is 1, meaning that 1 minus cos squared would be the same as sine squared. And this turns into sine squared. And you're thinking, hey, great, I've got them now looking identical. I have verified the identity. Well, unfortunately, you haven't, because when you did cross multiplying, okay, that only works when you have equality. Okay, you're assuming there's already is equality in place, and you don't have that here. Your job is to verify this. Right now, we're questioning whether or not equals applies. Cross multiplying would be inappropriate here. It assumes equality, and we cannot use any properties of equality. We can't add something to both sides. We can't multiply something on both sides. We have to kind of work on each side as its own, independent of one another. So is there a way around this? Without cross multiplying, is there a way to verify and show that these two sides really are the same? So I'm going to go back to the square one and Let me kind of clean this up a little bit here for you. Okay. And ask ourselves, okay, well, what could I do that would keep me from moving something from one side over to the other? Well, here's an idea, and this is what I meant by the idea of conjugates. If you think back to some stuff you may have done with complex numbers, imaginary numbers, you had something like 2 over 3 plus I. And you probably learned that you're not allowed to leave imaginaries on the bottom of a fraction. So one of the tricks was to multiply the top and the bottom by the conjugate. And when you do that, on the top it's pretty easy. It's just 6 minus 2i. And on the bottom, this is where it gets really interesting. 3 times 3 is 9. This makes minus 3i plus 3i. And let's see, I times I is I squared, so it's negative I squared. Well, these will cancel out. They offset one another. And this is just, this is negative 1 with a minus 1 here. That would be 9 plus 1, which is 10. And so you'd have 6 minus 2i over 10. And that's by using this thing we call a conjugate. This is the conjugate of this. You're able to kind of set up a difference of squares situation. And with complex numbers anyway, that's going to turn into a real number on the bottom. So this is what we mean by the idea of conjugates. Well, we can apply that same idea to trig verification. Now, I happen to see 1 plus cosine right here. The sort of conjugate of that, if you will, would be 1 minus cosine of x. And this is going to set up a difference of squares situation, which is going to pay off a huge benefit in just a few moments. But first, before we get going, we have to realize, well, now wait a minute, if I'm going to multiply the bottom by something, I have to multiply the top by the same thing. So I need, whatever I do on the bottom, I must do on top. Otherwise I change the value of that ratio. So this will be the first step, is to introduce this idea that, again, I'm kind of referring to as sort of the conjugate idea. Now when you do this, the top part will be sine x minus, and this will be sine x cos x. And that's all fine and good. Now that the bottom is where the real interesting stuff is going to happen. So if we now start to distribute, 1 times 1 is 1. Then we've got minus cos x. And then in this distribution, I've got plus cos x. These are going to eliminate one another. Notice I set up a difference of squares situation. And then cosine times cosine is cosine squared, and it's in positive times a negative, so it's negative cosine squared. Okay, so these will cancel out. That's absolutely fantastic. And then if you look at this, you say, okay, I've got 1 minus cos squared. Well, you realize that's really just part of the Pythagorean identity. Sine squared plus cos squared is 1. So 1 minus cos squared, 1 minus cos squared, it's probably better to say if I just subtracted the cos squared over here, 1 minus cos squared would be the same as sine squared. So I'm going to replace the denominator with sine squared. And so now what I have is sine x minus sine x cos x. And I want to show that, again, that it's the same thing as this. Well, now at least I'm getting closer, because now I've got the denominators to at least have both have signs in them. So where do I go from here? Well, again, we start thinking about how we start to simplify expressions. And there's things in common denominators, dividing by fractions, factoring and canceling. Okay, factoring and canceling can be used here. Up top, we have a common factor of sine x. So if I were to factor out that sine x from each one of these, so if I divide sine x out of here, I'm left with 1. And if I divide sine x out of here, I'm left with cosine x. And some of you might realize, hey, wait a minute, you're just kind of going back to where you started. In other words, had I not distributed the sine x in, okay, I probably shouldn't have done that in hindsight. I probably should have left that factor sitting out. And so now I'm looking at this over sine squared x. Well, now, because you've got factors, okay, here's a factor, and you've got 2 factors of sine right here. So we're going to divide out 1 factor of sine and take out 1 factor of sine here. And now we're left with this. Well, look at this. These are now identical, okay? So we can just kind of say, all right, I'm not going to do anything with this side. I'm going to leave it alone. And so I've got 1 minus cos x over sine x does equal 1 minus cos x over sine x. And so now I have verified, I have shown that the 2 sides are equivalent. So again, a nice little use of that idea of sort of a conjugate. So when you see 1 plus cos, you could use 1 minus cos. It's sort of for fun if you'd like to try, rather than mess around with this side, you could have taken this side over here, and I'm willing to bet you that if you tried 1 plus cos x here and 1 plus cos x on the bottom, I'm willing to bet that this too would have worked if you had kind of gone through and done this. And so on your own, if you'd like to give that a try, you're certainly more than welcome. So hopefully this gives you a little more information about verifying trig identities. Thanks for watching.